Welcome back to High Performance Computing, Scientific Computing. We have our lecture 7, Introduction to Deep Learning, the second part. And in the first part, we learned about some artificial neural networks. That's a technique that we know since a long time, is based in machine learning principles. It's one of the, let's say, rather shallow approach to learning today. And we will learn why it's called shallow when we look into more deep learning architectures, which is now the idea of the second part. However, the first part also was good to introduce at least a little bit of machine learning principles. So learning, learnable weights, how we can learn with a loss function in order to have the error essentially by using the loss function, maybe in a supervised manner, as we have seen with samples which are labeled. In other words, we have labeled samples that give us the correct output. And of course, every time we use, let's say in artificial neural networks, we can stick in a data element and we get an output. And then we can compare if that was the same output we got as a learning label is also giving us. So hence, we use this with a training set, train the whole network. And the training is really learning the weights. And the weights are numbers, right, as we have seen. But there are many of them, and this trainable, of course, factor in this is now the more parameters you have really in this learning from the weights, this will be getting more and more computationally expensive. Hence, there's the HPC part of it. We will now get into much more higher numbers of these parameters, as you would already probably think about. Still, it's good to understand from part 1, really, the move from the perceptron was basically then by adding different layers. And in these layers were all neurons. While the perceptron, this one neuron, so to speak, is just, let's say, one line in space. The idea of combining now, of course, many of these together in such a big network, we have seen 128 neurons in one hidden layer, interconnected densely, completely, with all the other ones in the other hidden layer with, again, 128 neurons. This 128 neurons is not a number that is by heart, so you can actually change these elements, which we call then hyperparameters. So it's not the parameters you give to the network, it's rather the hyperparameters where, you know, it's about the architecture, how many neurons in each layer. But then there are also other elements, of course, that we have seen with the learning rate. The learning rate, if you remember, was the idea in the optimization step to think now how quickly we move downhill, right? So stochastic gradient descent is one of those methods, which then use a learning rate in order to understand how quickly should I move down the error slope. And then this will determine, of course, also the progress in learning. While we have seen it would be in a way very nice to have a huge step forward in learning, we maybe overlook some elements in this path and come to local minima of the error slope, and then we're done. When we have a very small learning rate, when we have a very large learning rate, we jump back and forth in this valley of the errors and will never really find a perfect local or global minima. So also this is a sweet spot to find, where the learning rate is, of course, then also one of the interesting hyperparameters to tune your networks, setup, and so on later. So these are all topics which are alluding to hyperparameter optimization. So elements where also HPC is very strong. You will train the network with different parameter outfits and will also then in a systematic way understand what is your best neural network there. So hence HPC can be used in a way of really speed up the learning. So by using more and more GPUs in parallel, we also will see that the error significantly drops. But then, of course, also thinking about better models, right? So we think about better architectures by using HPC at scale, where you can have then different varieties of these parameters explored. But these are all rather advanced concepts of using HPC with AI. And in the light of the course here that we wanted to focus on CFD, and you know, this is something where we cannot put everything here in the course, unfortunately, but these are interesting topics where we publish also lots of papers. So if you're interested, just talk to us. So in one respect, we had really a nice introduction from machine learning, and now we will dive into the field of deep learning. Deep learning is loaded. It has many different models, many different architectures. Here we talk about the convolutional neural network, CNNs. So we will dive into these basics and will here and there point out what the point is now with deep learning in general. So I think many of you have seen these pictures. For instance, something like vision recognition, image recognition problems. You will find elements in the picture, essentially a lot of information that you can extract. And this is today really transformed, I would say, really with vision and also in natural speech with deep learning models. So here we really think about having, more and more advanced architectures of deep learning, not what you just have seen, a deep neural network, which then has different layers, and then we can use it, and we have all these different functionalities. So here we're going into a space where also these architectures have very specific layouts to solve problems. One of it is also this AlphaGo that you probably have heard, right? Which is a very specific type of architecture of this deep learning, or what you would see here a little bit by mimicking essentially with the physics of fluids. There are also different architectures. And wherever you go, in which domain you go, you will see there are a couple of principles in all of these which stick basically to it. One is that they all need quite some data to learn, and that they have all, let's say, specific architectures, but also they have in common that the learning theory underneath is also there. So that you're thinking about that you can overfit, you can underfit, as we discussed, not only based on data, but also on the amount of learning. Also the capacity of the learning models is something what we not really talked about much, but is a loaded element in it. So you can also have the wrong model for the problem if you want. So let's say if you have a perceptron learning model that we have learned and then want to understand protein folding, you probably have a problem, right? So you need the real architecture of these models, really, of this machine learning and deep learning space to solve these different problems that you have here. And equally, you would say if you have now, let's say, a very sophisticated gated recurrent unit or LSTM network with long short-term memory, which are used for time series, for instance, to mimic the fluid, and then you want to reuse that somehow to have our image recognition with the characters solved in the first part, this would be overdoing too much capacity, of this learning model for such a small problem. So this was also not really the right idea. Hence, these days, we have impacts a lot, but it's getting also more and more interesting to find out new ways where deep learning can, work. Many of you have probably also heard about this autonomous driving, which is a very interesting field, entering more and more based on deep learning elements, for instance, also in our practice. So in this sense, we have probably a future where lots of deep learning algorithms and models will be somehow placed as at least assisting drivers, and probably in the future also, on our streets. There are lots of tests around these days everywhere. The most limitations which are here faced, I think, in this area is one example, again, is also law and legal aspects. So what happens if, the car has an accident or the deep learning is misfunctioning and drive the, so to speak, the car to the wrong destination, or is overlooking, let's say, a kid on one end of the street and then grown-ups on the other end of the street. So this is something where, this is not obvious, this legal question still. So I think this prevents a bit entering that really into it. And of course, we all as humans, and this is now my final part in this slide, we all as humans have a sort of natural criticism with this because we don't really understand it. This is called causality. We want to understand it, causal, elements in it. So in this sense, if you remember what we had in the first lecture, here in the first lecture part, where we said, okay, the perceptron has a couple of weights. They are 0.5 and 0.7, and that's why it works. And so what? It works, okay. In so many probability of the cases, 97%, okay, 95%, okay. But we didn't really could explain why. It's a sort of black box, especially if you think now about this hidden neural network that we have with two hidden layers, right? So there were 128 and 128 neurons. They all got their different weights in the interconnection with a dense layer. We learned this and it worked, very high percent, okay. But why now the 0 or the 8 is, let's say, a little bit better, than before in the perceptron, kind of in the accuracy, we don't really have the explanation for it. We just know that maybe here and there are weights that then essentially give you, instead of a 0.5, maybe 0.6. Congratulations, you won a lot of this. So what happened? So I think this is one of the challenges I want to allude to. This criticism also, when you think about you want to apply now this assistant not only on our roads, think about you want to apply this in medical robots, right, on the operation theater space. So naturally, we humans will say, well, can we trust this? Is that working? Which is now one of these, let's say, highly debated elements of deep learning you also should know. So it's not that we all technologists think, well, let's do deep learning for the rescue of human mankind, push it ahead or use it in gaming, and it's done. So there are huge research projects underway in the field of understanding of this deep learning elements. And there are even professorships built on this basis, which means something like explainable AI, the explainability. So you want to understand why the network is taking this or that decision. And there are techniques around it, like where you can at least understand a little bit where the weights are changed, why this picture has been classified for that particular label or so. But this is still a domain in its infancy. So we are still trying to understand deep learning better. There was a huge technology advantage based on our GPUs that we have, that we can calculate deep learning on scale massively. We added more and more layers, more and more complexity. But the kind of explainability from it is really what we suffer these days. And there's much more coming, hopefully also. And this will be a key element then also to put it in our practice, right? Like autonomous driving again, or in operation theaters, at least at assistant, right? That is something to think about. And I could talk on and on. As I said to you earlier, deep learning should be a whole course. So how can I possibly put that on one slide, right? And a couple of other slides which will now follow. But in a way, I really have to cut this into a very specific area. And this is what this also entails. Here you have a very interesting slide. I was doing this slide once for the, for German politicians. They asked me to put one slide, please, with HPC, clouds, big data, and also machine learning and deep learning on it. So in a way, all of that together in one slide and having 3 minutes to explain it. So that is this slide. And I got good feedback from it that it captures the essence quite well in the amount of time. And what you see here now is a very important message, how it is related now to computing and all of the other elements that we have here with other machine learning models, as we call that. So let's start with this, where you think about, first, we have to think always about the data set, right? Machine learning means learning from data. Hence, our data set is a key element to think about. And then, of course, we're interested in doing model performance and better accuracy. So that's also important. Hence, what you will see here is that we will use different models in this slide here to achieve better accuracy, but then we also have to pay the price for it in data, and it needs to be available. So, and this is exactly the field where then the traditional learning models will still play a role, especially if you, let's say, don't swim in data, right? If you go towards the right here to big data, you will notice that today in really applications around engineering, medical domain, sometimes or many times the labels are missing. right? You have unsupervised data, or the amount of data is simply not too much, right? Think about innovations for rare diseases. Rare disease patients, by definition, rare means they're not so much data. So in this sense, you have problems of finding big data in terms of volume, for instance, right? But could be about many V's. Actually, this is a characteristic of this big data, which we also teach in the other cloud computing and big data course that is actually coming in fall, if you're interested. But here, take away the message that the traditional learning models that are existing, like support vector machines, random forests based on decision trees that you see here, they all play still a role today. And the reason is because we are not having every time very much, let's say, data sets. So also, however, the problem is if you have too much data in this domain, and you want to use, let's say, these elements, you have some, let's say, traditional tools you usually use with them, SVMs with MATLAB, or you use them in scikit-learn, so more serial ways how to compute elements, you will quickly see that big data will crush your laptop because you cannot just have observations in terabytes and terabytes actually loaded into laptops. Hence, here we see the first footprint alluding to computing, to high performance computing, which you see also a little bit here with the training time. Sorry. Here that also, of course, here the memory and the training time is an important factor in it. However, if you think about that small neural networks are not far off. So what we have seen, the two hidden layers, this is a kind of sound technology that by lots of tuning, you come to very good, let's say, results as well. Still, of course, if you have a very sophisticated network with two hidden layers and then have 256 neurons, for instance, in each of these layers, you still need to have a certain amount of data, right? Because you have so many trainable weights, you have to have the data to fuel it. And this is something where we see the small neural networks, and the footprint really of this learning is still not too high, as you see, right? We're still speaking of this area. Now, then, of course, as the footprint suggests, we're carrying on to medium deep learning networks, something we will do today here in the CNN space, for instance. But there are much more sophisticated models that are rather here with large language models, transformers, and so on, and also bigger residual networks, where the computing time actually is always increased and requiring high performance computing more and more. Talking not only about training time, but also the capability to take also, of course, all this big data into memory. But you see also that the accuracy then will always rise. So we see their potential. If there's big data and large data sets, there's a high chance that cutting edge deep learning models, for instance, will beat what we have here below. For instance, vision transformers and so on in this space these days are quite here in this area, which have really extraordinary performance. But if you feed these transformers, let's say with less data, you see that significantly the accuracy will drop quickly. Even if you are in this space, and this is another element which I wanted to talk to you a little bit before, then it can be very well that here this ordering, of the accuracy having this slope will be really dropping off into the zero. And it could be that a random forest, for instance, is still pointing very well and is much better than a deep learning network, just because there's not enough data. So there are lots of, let's say, hidden treasures in this. And one of that is another element I wanted to talk about. This is this manual feature engineering, right, that you see here. That changes, of course, really also the ordering, if you want. So this is something where you can, of course, create your own features. You derive, let's say, very specific elements from the data. And you did this manually in the times, let's say, of SVMs and random forests and so on, a lot. But nowadays, these deep learning networks have also a sort of kind of learning inherently, which we call then essentially this feature learning aspect. So you don't craft a lot on the data anymore. I mean, you still have to clean it. You still have to, prepare it in the right data structures to be read by the tools. But sort of not really thinking about lots of different elements, like involving, for instance, the neighboring pixels in one pixel classification and things like that. So this is something to think about. And I hope here with this picture, of course, you get the message that really deep learning is powerful, but you have to have the data for it, but you also have to pay the price for high performance computing. And here I make also the cut, I mean, basically to the cloud computing environments, right? So of course, this is also something which can be done here and there in clouds. The difference between those will be also explored more in the cloud computing course, hence the marketing again for our fall course if you want. But I want to end up this, of course, with some interesting element, so-called the Nobel Prize of Computing. You see here from the inventors of the, kind of deep learning approach. While deep learning was there a long time in a way, these gentlemen that you see here are very well known in the AI domain, and as such also brought this field of deep learning really to a, let's say, critical element. So we see more and more applications on it. We see also, as you've seen within NVIDIA, that it drives even technology uptake, right? So the GPUs, as we were alluding to in the last lecture 6, which is fueling deep learning a lot. So in this sense, this was definitively an interesting award. But let us look now again to some of the aspects of deep learning. And this is something where we have to come back to one of the slides where I show this again. Some of you have already seen this, so let's play the video again a little bit. So, shortcut. You have seen now and better understand what we meant with perceptron, right? You have seen this in the first part. There was not this layered architecture that you see there. This was just directly giving then you through the softmax, the last layer, so to speak, out the probabilities, which is always this firing here that you see at the end from this. Now you see nicely also this multi-layer perceptron here, right? When I stop it like this, you see the dense network, which is another important element I wanted to convey now when we talk about more in depth what deep learning is. So we had the hidden idea with the dense layer, if you remember. Dense in layer is referring to something you see here, that all the input layer neurons are connected to all the neurons in the hidden layer. These are all connections, right? Every one to every other one. Hence, this is a fully mesh in a way, as you would call it. And this means all trainable weights that have to be over time trained. And of course, it gets on through the network. If you think now here, the bigger architecture, you would connect this hidden layers again to the output layer, right? If you do it with one hidden layer or you have here two hidden layer, doesn't matter. We would consider it as densely connected. In other words, every neuron is connected to the next layer, also to every other neuron. And this is now an important element to keep in your mind when we talk about convolutional networks very shortly, right? Where we stop using densely connected networks to some degree and basically put something in which is a bit more, let's say, smarter. Hence, however, we still use the elements of that in the end. So let's continue a little bit with the video to contrast it now of what we want to do with deep learning. So here you have now an interesting perspective. So interesting in one respect, because firstly you see suddenly we have there the image still as an input, but not directly just dots and neurons. So in other words, we keep elements of this image, the neighborhood, to some degree, something what we then call feature maps, right? So in the end, what we will do is a little bit explained here compared to this part of this element of the video here, is the so-called feature extraction part. And this is now pointing to the fact what I talked to you before, that in previous times in traditional machine learning, we were crafting several different features, right? So working on the data, putting in the neighborhood pixels to some degree for one pixel, if you want to classify, let's say, one pixel. And then we learned the model, and then we did, basically more with it. Now, what the deep learning element is in it is that it so-called has this feature learning inherently. So it's part from the model a little bit to extract these features, to find these features, to learn these features. And with this, you come to a situation that you can work still on the data and create your own filters and the element. But we want to understand what exactly now happens here, right? I was alluding to this a little bit already in earlier lectures. And of course, here we're still talking about trainable parameters, right? So that will be all still trainable. And we will dive into this in the next couple of slides. So don't worry to not understand this yet completely. Just that you get the notion that this deep learning networks that you see here now has two parts, the feature extraction part, but still then also the classification part. And as a surprise for us, this is still fully connected, a big mesh, right? And this will basically not change if you talk about this multi-class classification. We still have a, let's say, fully classified element or fully classification at the back here, which is essentially in this video the idea why this is there. And there's still also the softmax that you know now from the lecture 1 parts, right? The softmax was then the function that brings the class probabilities between 0 and 9. And then we said, if you take the winner takes all route, that means the highest probability wins. Although, of course, when you think about learning, it could be also the case that many of the digits look similar, like a 9 and an 8, depending on how accurate you are writing, you could be misled. And some of the elements would be probably never learned, because this is something where you think about this is hard to learn anyway, because we humans don't even know what it is. But to do this feature extraction mechanism enabled very interesting networks. You see here examples where you can recognize faces even if they're just partly an element, because they have the same concept here that over the feature extraction, you extract features from human faces, like eyes, ears, noses, and so on. So the same principle applies, basically. So let's dive into this a little bit. And of course, convolutional neural network should be a lecture on its own completely, maybe even two, to really understand the whole power of it. But let's keep it simple. Coming back to our example, we had 28 by 28 pixels. So what we had before is we vectorized it in a very long vector. Here we keep it now to this element. We basically put the digit in, and we will connect it then now with this little window here to the next hidden neuron. And this is something which is one of these kind of elements. Now you can see that the neighborhood on one pixel is still, so to speak, a little bit preserved by the elements you learn and connect to the next hidden neuron. We call this local connectivity that you have on this data. So you kind of have not lost anymore the context of your surrounded pixels, but you keep that for some respect when you go to the next level of feature maps. You apply a filter, however, that you essentially see here. One idea is then how this convolution or the convolve feature will then be established. Here's a filter example that you see in orange that is taken here over, basically over this input space of the image. Here's a, 3 by 3 one, and then you compute this and have a convolved feature. This is, of course, just one step in the very, very big convolutional network, but it's a key element in it that, you do this again and swiping basically over the input space. You see, doing this with the first neuron in the hidden layer, doing this then further, shifting one in the second neuron in the first hidden layer. And this is something which we call a filter that we apply to this, that you then, of course, also learn. You see here, when you look at this example here, that you still have weights in it, and you apply a set of weights to this filter to have this local feature, right? Like could be an ear, a nose, whatever is behind here. And that is something what you want to learn. So, of course, there's many hidden gems like padding, if it doesn't fit with your filter, your picture, and other elements. And then you have, so to speak, a local representation of these features when you have this activation of the filter, when you, for instance, just use it, right? You, of course, have one way of just using the network. Then, of course, your local feature will, ping, or your signal will be starting and saying, well, I found an ear, when you basically come with these local features of the image. Of course, it's a bit more deeper. So we have seen it's a much more deeper network character, hence the name, where we do this iteratively, right? You see this quite nicely if you have this typical example of having a car to recognize, right? You have a convolution and rectified linear unit operation, and you do pooling again. And then again, convolution, rectified linear unit, pooling. Pooling stands for reducing the amount of data in this particular step before. Could be average pooling, could be max pooling. The max pooling stands basically for the strongest signals survive. However, how you do it then to come from the step here from the initial car or in the subsurface areas from the next convolution or operation is always shown here. And in the video that you have seen, it's not necessarily just one feature that is crazy. Of course, we have many different features, right? How we recognize cars and how we want to do this. So we could say of creating, let's say, different feature maps, which will be all, let's say, in the array from all this multi-dimensional array. You have to see now for the weights, right? Because we have here 3 inputs, could be RGB, for instance, if you want. And you see here how the filter is applied again and goes over it. And here also a little bit of padding needed, perhaps, here to get this to this image. And when this is successively done again and again, you will see that the features will be much more crafted and getting more and more simpler, right? Where, let's say, elements of the overall car will be getting, into tires, into front lights, and then maybe even into parts of tires and smaller elements. And this is now the success of these networks, because it really recognizes the features. And the interesting aspect of it, given this weight sharing principle, right? We don't talk about necessarily here a fully connected network anymore, but rather only at the end, right? Here we're talking about this weight sharing. That means you actually can detect the feature everywhere in the image. So even if the car, let's say, has a crash and the tires are up, you would say, well, it still will be recognized as a car because these are tires features, even if the car is strangely put, not on the road, but other way around. And that gave basically one of the key successes to this, convolutional neural networks, which were and are still very powerful. One way to do it yourself is when you want to, let's say, play around a bit. Here's one of the interesting tools in the references where you can draw yourself a number, and then you see nicely how the feature maps are successively going through the different layers, layer by layer by layer, right? From input layer to all the different elements. You see the pooling effect of having reduced data, smaller and smaller. And then here the fully mesh at the end to recognize it again as digits. So I encourage you to take the course at this website quickly, do a couple of numbers. It's quite insightful to do this, and then play around maybe also with a 0 and an 8, which basically are quite overlapping in painting. You will see some surprises. So coming back, however, to our real code to show some influence and then finally get the connection to HPC again, because of course I could talk now ages about the CNN model, how it exactly works from the deep heart. I think we keep it at this level and thinking about rather what it now costs in terms of computing, right? So you see here again, Keras model on the CNN. We had the sequential before, but now we add this convolutional 2D elements. So we have 2D layers, right? Not any more just neurons. We have this kernel sizes we discussed, of which we go through them. And padding remained, again, the point of saying how much we need to fill the image. And then we have the activation function that we already know, ReLU, rectified linear using. And then we apply a max pooling in 2D, 2 by 2, and then strides going, let's say, over the image again. In other words, the strongest signals will be kept here in order to, let's say, make the data a bit more smaller. Oops, sorry for that. And then we come to the next level, another convolutional layer, right? You see that nicely here in Keras how we can differentiate this. So we have another convolutional 2D layer, which is then here. But here we add 50 feature maps, right? So maybe there are more features when we, let's say, have smaller features to think about in this application. That's also, of course, a more or less application domain question, what you do here. And then again, have a max pooling there. The interesting thing, however, then how we end this is in the space of a dense connected network, right? But you already know that we will flatten this, so vectorize in one way. And then we have a dense layer, really, with a rectified linear unit as a, let's say, last element before we now enter into the decision making, so to speak, which class it is. And the decision making, as you know, is done again with a softmax operation. And more or less, this is then the output layer here, right? So in the end, we have still a fully connected network at the end, which gives us then quite some parameters. But of course, as we have here also quite some feature maps, etc., that all have different connections to the previous layer and then to the next layer, we're talking now about a massive increase of trainable parameters. We're leading here with this very simple network, really, to 1.2 million trainable parameters. And now, when you now think about large language models and the domain where we are in cutting edge with deep learning, we're talking even about much, much more, not millions, we're talking much more, billions of training and trainable parameters. But here for this, we pay the price. We have more trainable parameters, significant more. If you remember, we had around 100,000 for the hidden neural network with 2 layers. The neural network with 2 hidden layers, so to speak, was giving us quite some decent performance, but still the computing was not so tough as we see it now. We still have to think about now to change a little bit the code when we want to see the details. We remember now we don't have to vectorize, we stay in the 2D domain, but still many of the elements you then know from the way how we compute it is actually something you already know. We train for 20 epochs, we have a batch size of 128. This time we use the ADAM optimizer, which is essentially an advanced optimization techniques that has a much more momentum in it. So how much you really go downhill and speed, so to speak, which will be reused. It's an optimization as well and similar to SGD. Then we have validation split. So there's also the concept of validation in, and of course, then the 28 by 28 pixel elements here. The other ones are loading the data, normalizing, as we discussed, and so on. But then we come quickly to the idea of thinking about what is now the win of it. And the win, you see, is quite obvious here. So we have 0.99 performance. So 99% with a deep learning model for this simple toy problem. But what is a bit hidden here is that the training time is now significantly more in terms of GPU usage, right? In other words, those that do the final project in this area will certainly realize that for using CNN with a CPU, that is not really a good choice, right? Deep learning models like the CNN really flourish with, GPU power, as we discussed with the many cores in lecture 6. Hence, there's a massive difference, and the reasoning why we need this computing is really then set in the trainable parameters, because here much, much more with 1.2 million parameters. Hence, however, we win, we get better performance, which could be quite a good application output. If you think about improving just a couple of percent could make, let's say, a big improvement for your customer. Let's say a bank and interest rates, or for instance, Netflix that wants also channels of making their recommender system just a little bit better. So this is all, you know, the win still at a couple of percentage can mean a lot. Now, also finally, the limits, of course, you see here, 100% is basically also not even for the cutting edge best deep learning model possible, because some models, or some digits out of these are just samples which we call noisy, which actually humans can also not really realize. So it would be also strange to learn from this. We put that here in the Jupyter notebook as all at one code, so that you see again the overview, how it all comes to. You will also realize that apart from the model, we have then different elements, and you will see the epos, how it trains here, all, you know, step by step by step. And as I was earlier saying, CPUs, will you notice, will be doing this very, very slowly, while GPUs, you see the arrow, you see the bar really progressing very quickly. Hence, a very important part, and also the fueling of deep learning. We would love to teach much more in this area, but I think here this year we really do a CFD course, and there are many other courses around that do deep learning really in deep detail. So for us, it was good to know and to understand more parameters means more computing is needed. And for those of you who want to also experiment with this a little bit, you see here the Google Collaboratory cloud infrastructure that is for free. And if you spend just $9.90, then you get even a bit more sophisticated GPUs and so on. But think about that the source codes that you had here and there cannot always be put from one to another. This is a problem with porting we were talking about earlier. So hence, it could be different GPU, you know, times, but also, of course, the source code is in TensorFlow 1, while now there's maybe TensorFlow 2. So different software packages could be also some reasoning. Just for you as a pointer that if you want to use it and experiment with it, the Google Collaboratory is at least also giving you one GPU, not at scale yet. And for machine learning theory, again, I would really recommend you to go to a proper course in machine learning. That's important to understand the basics a little bit better than I could convey today. Then you understand also better underfitting, overfitting, and these elements. This video gives you a short, let's say, crash course in it. Again, what these terms are, but in a way, what our main aim is in machine learning is not only learning from data, we combat overfitting a lot. And there are principles like validation or regularization that we will apply in order to do this. So hence, look at this video maybe a little bit to understand these terms better, but consider really to do a course in this area if you find it interesting. So, and that's all for this, let's say, really small crash course to deep learning. We will continue then with another application area in CFD next time.